Okay. So we're going to move into looking at probability distributions. Gentlemen. Thank you. We're going to look at probability distributions. There's two different types of probability distributions. Chapter 7 is going to be looking at discrete probability distributions, and then chapter 8 will be looking at continuous probability distributions. Anybody remember what the difference between discrete and continuous is?
There are breaks between the data or not, or if it can go between every number between.
Yeah, discrete is specific values, like 1, 2, 3, like those would be discrete values. If I can do everything in between them, that would be continuous data. So, all right, so a couple pieces of information that we need to look at, or definitions. First one is a random variable is a numerical outcome of a random process. So basically a random variable is what we're going to be looking for, not a specific value. So it would depend on which ones we're going to be looking at. And the probability distribution is which describes that specific kind of random process. Both those sound complicated, but as what you've seen so far, at least I hope, they sound really complicated, but once you actually start doing them, they're not nearly as complicated as it sounds. Give everybody a chance to finish writing those down. All right, let's look at a discrete random variable. So a discrete random variable is a random variable which has a countable number of possible outcomes. So when you're describing a discrete random variable, we need to do the following three things. We need to be able to state what the variable stands for. We need to list all possible values of the variable. And we need to determine the probability of these values. So for everyone we're going to look at, these are the three things that we're going to have to state. All right, we'll look at a simple one first. Oh, yeah, sure. What's that? That's fine. You're welcome. We good now? Okay. All right, so let's look at a simple case. So tossing a die. First question is it discrete when we're rolling a die? Or is it continuous? Is rolling a die discrete or continuous?
Continuous because the whole range of the die.
Can I get 1.5?
No.
That it's discrete. Remember, that was really the thing we used between them, right? Can you get a half of it? If you can get a half of it, start thinking maybe continuous. Not always, as we said back when. But in this case, you're going to get 1, 2, 3, 4, 5, or 6. There's only 6 possible outcomes, nothing in between them. So this is a discrete probability. So we've determined this is discrete. Is rolling a die random? Yes, we can't predict the outcome, right? We're talking about what random is last time. So rolling a die is a random phenomenon. So we can identify the 3 pieces of information. So what is the random variable? So what is the thing that's going to come every time I roll the die? Is the outcome, right? So my random variable is the outcome of the toss of the die. So that is what my random variable is going to be. So we notice the random variable is basically describing what the outcome is. It's not giving me the list of outcomes. That's the next one. It is just describing that. Once we can describe what the variable is, we can state what the range of values are. So in this case, when you're rolling a die, we're going to assume it's a standard 6-sided die. The integers are between 1 and 6 inclusively. So you can state that, or we can literally, in this case, you can actually list them out. You can say it's 1, 2, 3, 4, 5, 6. And that'd be a totally valuable or totally valid way to write the range of values. It doesn't necessarily have to be written out in words like that. Probability distribution sometimes is difficult, or sometimes you actually can't do it based on what random phenomenon you're looking at. In this one, we actually can. So you'll notice that the first line here is x equals. That is your variable. That is your random variable. So we have 1, 2, 3, 4, 5, and 6. The probability of each of those, you'll notice that this is how it's actually written. This is the probability that the random variable is whichever value those x's are. I know it sounds weird. It's a big X and then a small x. It's not the same size as x's. That's the symbol you're going to see when it's written like that. What's the probability of rolling any number on a die? 1 out of 6. And you notice that that's the probability distribution there. Yes.
I assume all of these are going off of theoretical, right?
Mm-hmm.
Okay.
Well, yes and no. This is. Not every situation that we're going to look at would be based on that. You'll see that in the next ones. Because theoretical means that we have a set amount of it. A lot of times, sometimes we don't have that. We would have to collect the data to be able to figure out what our probability distribution is. The other thing we're going to look at is, hold on, I need the actual word, and I can't think of it right now. Is a uniform distribution. So some things are known as a uniform distribution, and some things are known as a non-uniform. This is exactly what they mean by uniform. All the values are exactly the same. Okay, so if the values went up and down, that would not be a uniform distribution. So we will look at a couple other situations of that later on. But when they ask for a uniform distribution, this is a uniform distribution. I just taught you all of 7.3. That was literally what 7.3 is. Is this a uniform distribution or not? All right, let's look at this one. The number of defective integrated circuits received in a batch of 1,000. Now you can see why they're not always going to be theoretical. What is the random variable for this? Yeah. Yeah. So X is number of defective. What would be the range of values that I can have for this? Not you. What's the range of values I can? Yeah. Almost. Oh, so close. Not 1. It's 0. So technically, we could have no defective circuits in the entire 1,000 batch. So my range of values is from 0 to 1,000. And I probably spelled inclusively wrong, but you get what I said. All right. What's the probability distribution? From the information they gave you, do you know it? No. So this one's unknown. Because this is more of an experimental probability than a theoretical probability. This is one of those ones that we'd have to actually look at historical data to be able to figure out what's possibly going on. But that is an acceptable answer for this one. Do you think this one would be a discrete or a it is discrete. Do you think this one would be a uniform distribution? No. So, because not every value is going to show up the same amount. Okay. Good. All right. So this one. So they're looking at the number of babies born. So my random variable would be the number of babies. Is this discrete? Yes. Cannot have a half a baby. Okay. So the range of values are integers from 0 to some large positive number. Does that go against the definition of what we talked about? So remember what the definition was. List all possible values of the variable. Did we list all possible values of the variable?
Feels like no.
Okay. So this is one of those ones that, like, because we cannot know what the upper value is, but we know there is an upper value. Like, you're not going to have an infinite number of babies. Like, there is some upper level that we're going to get to. However, we don't know that specific number, so they're not going to put a specific number there. But because we know it, you still are actually stating all the values. Does that make sense? Okay, that's why I put some of these, like, these type of situations in there, is because, like, we can have that conversation like, okay, is this or is this not? Okay, because again, it's just some randomly large number. It's not necessarily, we still aren't counting them. All right, so a restaurant has expressed a policy that states lunch will be served within 15 minutes of ordering or it is free. So what is the variable that, what is the or random variable that I'm looking at? Yeah. How long? Right. Okay. So X is, what's the range of values?
I don't know what the shortest time would be to cook, but assuming they have it like somehow instantly ready, maybe 0 to 15 minutes, continuous.
Why did you, so, okay, 0 is totally correct at the beginning. We're going to assume that there could be like sandwiches there that they can just hand it. So we're going to assume that 0 is an acceptable answer. Why'd you stop at 15 minutes?
With the outside the window they were looking at. Like they were only looking at how it has its policy on what time they're allowed.
Right. But could it take longer than that and they would just have to give it away for free? Yeah. So it's 15 minutes isn't the end. That's just where they're going to start being for free. And in essence, they're looking at what's the probability that that's going to happen. So that's kind of what they're looking at in this case. So we do want to go higher than 15 minutes. But do we want to go to infinity? No, again, this is one of those ones, there's some arbitrarily large number. Like if we're talking about minutes, if it's lunchtime, like 3 or 4 hours probably is outside of lunchtime at that point. So 0 to a large number. So it's not going on to infinity. It's just some other randomly large number. Now, hold on one second. Is this continuous or discrete? Why is this one continuous? Right, but it's still a continuous time. Like that's the whole thing. Of like, if you're talking about money, like is dollars and cents continuous? Most people would say yes, because like technically you can't have a half a cent, but same thing with time. Time is typically considered continuous because you get down to seconds. That's where we stop really counting time at that point. So it's still continuous in that respect. So that's the difference between the continuous and discrete when we're looking at them. Notice that the value, like how we set this up, is the same. It's not going to change anything there. It's just that it's measured on a continuous scale instead of a discrete scale. And again, my probability density is unknown because it goes on forever. All right. What to classify as a discrete random variable or a continuous random variable? The total points scored in a football game. Discrete or continuous? Are points discrete or continuous? There's a lot of you in this classroom, and I know the answers these are pretty simple to do. So somebody else speak up. There's like 4 of you or 5 of you that talk. Discrete. Why? Right. You can't get half a point. I'm trying to think of actually, is there any sport where you can get a half a point? I don't think so.
Performance type ones where they have to average 3 numbers.
Yeah. But even those tech, like, yeah. I would even say those are probably discrete because typically most of them are like halves or like it's like that. So we're going to go with discrete for that one. Something tells me cricket you can get a half a point, but I'm not sure. It's like, but I'm not sure. Like I can't. I know, but I'm like something reminds me. Like I've seen a score with a half. The daily price of a stock. Discrete or continuous? Yeah. Price of a stock is money. Money is typically considered continuous. Interest rate charged by local banks for a 30-year mortgage. Discrete or continuous? Yeah. Number of times a backup of a computer network is performed in a month. That's discrete. We can't have a half a backup. The amount of sugar imported by the U.S. in a day. Why?
Actually, no, it is.
Yeah, I can have a half pound of sugar. Yeah. Yes, this one's continuous. Don't change because I asked why. Yes, that one would be continuous. There was I. All right. Let's specifically look at discrete. And these are all going to be probabilities that, or distributions that I could actually find the distribution for, or I'll give them to you. So, a discrete probability distribution. There's 2 very specific things that has to happen. One, the sum of all probabilities has to equal 1. And the probability of any value must be between 0 and 1. That goes back to what we talked about with probabilities. Remember, probabilities have to be between 0 and 1 inclusively, and all of them have to add up to 1. So discrete probability distributions are going to hit the exact same criteria. All right. Tossing a coin 3 times. Remember, we've done this one a couple times. First question. Is this a probability distribution or a discrete probability distribution based on this? Let's see if I can make this a little bigger. Okay, so the probabilities add up to 1, and they are all between 0 and 1, correct? Okay. Is this a uniform distribution or no? Okay. Why? Correct. Good. They're not all the same value. We have 1/8, 3/8, 3/8, and 1/8. Very good. Okay. All right. Let's look at one that's not dice or coins. So during the last year, he's kept track of his computer sales for the last 200 days. He recognizes his daily sales constitute a random process. Do you agree with that? Can he predict how many he's going to sell the next day? No. So therefore, that by definition is random. He can't predict it, right? Okay. From the probability distribution, he'd like to determine the following: the probability that he'll sell at least 2 computers each day, and the probability that he will sell at most 2 computers each day. So we've got our frequency distribution. We need to come up with our probability distribution. So how would we come up with the probability? How do we determine how many times he sells no computers? Somebody that hasn't spoken today. Nobody? Do we need to go back and actually explain how to do probability? Or are you guys all just way too scared to actually say a number? Okay, the normal 5. What's it going to be?
So for each, I mean, we should do the chart first, right?
Yeah, we're going to have to start the chart
So,
first.
probability of 0 would be 40/200.
Yep, all we're going to do is take that and divide it. So
Simplify to what?
I might make these as decimals because they're actually come out even numbers.
Oh, right.
So 0.2. 20 divided by 200 is 0.1. Because these decimals actually end and they're exact, they're easier to use as decimals than leaving them as the 0.2 and then 0.9. So those are my probabilities that each of those events will occur. So what's the probability that he'll sell at least 2 computers each day? So which ones are we going to be looking at in this situation? Ones with 2 or more. So we're going to include the 2. So what's the probability that he'll sell at least 2 computers each day? It's going to add those probabilities up. So 0.3, 0.2, 0.2. So 70%. What's the probability that he will sell at most 2 computers each day? Which ones am I going to add up for this one?
Also included that one too,
Yes, because it says at most 2.
0, 1.
Right. So we're going to be at 60%. Are those complements of each other? Why? Complement, if you add them up, has to be 100, right? So in this case, these are not complements of each other. They overlap at the 2. If the 2 wasn't included, if if it said sold less than 2 computers each day, we wouldn't have included the 2, and then they would have been the complements of each other. But in this case, the 2 is looked at twice. Is this a uniform distribution? No, they're different numbers. An investor has decided that she'll purchase stock if there's at least a 50% chance that the stock will be more than $32 in 30 days. Assuming the price of the stock 30 days from now is described in the table below, should the investor purchase the stock? Yes.
First of all, what is it asking here? Like, what is the probability of the bottom? Like,
So,
I understand the top is the range of prices it can go to, but
okay, and then the bottom is going to be my what? That's my probability
the
distribution.
chance of it happening.
Yes, those are the chances of each of those prices happening.
I wasn't sure where the initial. So,
Yeah, I based on the question, they didn't give you any of that. So, so those are the stock prices, and those are the predicted values of that they would occur. Totally made up, because there's no way you're going to know this 30 days out. You can look back at historical trends and stuff like that to get some idea, but it's still a guess. All right, so based on the question, she wants a 50% chance that it'll be more than $32. So which values am I going to look at that say it's more than $32? Am I going to include the 32? Why? Did she say at least? She's at least a 50% chance, right? But it says more than 32. So this is where, remember I said back, it's going to be an English problem a lot of times. Like, this is where that goes in. If it said at least $32, you're absolutely correct. We would have included the $32. If it would have said 32 and more, include the $32. But since more than $32, we're not going to include that $32. So in this case, we're just going to look at those 2. So what's the probability that it's going to be more than $32? 0.20, right? So is she going to invest? No. She's not going to invest. All right. Let's do it that one before I go into expected value. All right. Expected value. What's that symbol mean? That little, yeah,
oh,
that symbol.
That's the mean.
That is the mean. All right. Just think, it looks like a cursive M. Let's see if I can actually. I think M had 3 loops in it, right? So it kind of looks like an M, right? So think that in mean. It actually is the lowercase mu. the Greek letter mu. So how do we find mean typically? Very good. So we're adding them up and dividing, right? That's how we find average. How did we find when we had a what was the word? How was it called? A weighted mean. What was the difference when we had a weighted mean? Like if you're going to figure out your grade in the class, are you just going to add up all your tests and divide by 3? Is that going to be your grade? No, because you have other things, right? So the weighted mean was we had to multiply by however the percentage of those pieces, right? Or how many of those things we had. That way we didn't have to sit there and count them all out. Expected value basically does that. An expected value is kind of like a weighted mean, where the weights are the probabilities of that event occurring. Okay? So you're going to multiply each value times the probability, and then you add up all those answers, and that's going to give you your expected value, or in essence, your weighted mean. Yes.
Is the E there meaning the sum? of
Yeah,
jump?
that's
Okay,
those.
I'm sure.
So that right there, that's sum. That's sigma.
Simplified to the E, like you can write it as E.
No, so that E right there stands for expected value.
Oh, okay.
So this is technically the formula for expected value. All right, so let's look at the sales ones we just did. So remember, we had our X's and we had our probabilities. So the expected value, I'm just going to multiply those two. So 0 times 0.2 is 0. 1 times 0.1, 0.1. 2 times 0.3, 0.6. 3 times 0.2, 0.6. 4 times 0.2, 0.8. And then we add them all up. And I get 2.1. That's the expected value. So based on his probability, the expected value is basically what he would expect to sell each day. So he should expect to sell about 2 computers every day. That would be his expected value. Some days he'll sell more, some days he'll sell less. But on average, he would expect to sell 2 computers each day. That's what expected value is. All right, find me the expected value of option A and option B. Yes.
What do we do for zero?
You sort of, it's basically going to be 0, but you'd multiply it. So the expected value of option A is $900. The expected value of option B is $1,400. So which one's a better investment? B. If the probabilities are correct, you are set to make more money investing in option B on average. Now, this is the major question when you're looking at a this is still technically a theoretical because we're just giving you the probabilities, is that if you're only doing this once, if you're putting it in there and investing, it's like, okay, that's going to be your profit. Option B, you have a 30% chance of losing money. Where option A, you only have a 20% chance of losing money. So the expected value is if you're doing it over time more than once. Like that's what you would expect to see in the long term is 900 for this one or 1,400 for this one. All right. We also can find the variance and the standard deviation. You are not using these formulas, so don't write them down. What is standard deviation? Tell us. Yeah. Yes, how far it's varied, right? It's that variance for it. I know this one's called variance, and the standard deviation is the square root of it. It's basically telling me how varied the actual information is. I will have this site on my website. This website has a probability distribution calculator. It will allow you to find the mean, the standard deviation, and the variance. How you do this, the very first one, you're typing in the values. So for the one we just did for A, it was 2,000, 0, 1,000, 2,000, and 4,000. And then the probabilities of each of those occurring. 0.2, 0.1, 0.3, 0.3, 0.1. These have to match. The number of values here has to match the number of values in this one. And then you just click what you want. So we're going to find the standard deviation. And you calculate it. And it gives you the answer. So the standard deviation for this one is 1,757. Yes.
What is this titled on your website?
It's called probability distribution calculator. It'll be on the link with the class notes and stuff from chapter 7. And the same thing like I did last time with the test, I will post it up there for that test one so you can have the calculators for the test when we do chapter 6 through 8. So that is and notice if you ask the standard deviation, it gives you the mean because it has to figure out the mean. It also gives you the variance because it has to figure out the variance, and then gives you the standard deviation. So it's all kind of put together in one. Okay. So We go back and look at what I had here before I deleted it. So there's the mean, standard deviation, and variance. What do you notice about the standard deviation? So the means are exactly what we came up with, right? Is the standard deviation for A or B bigger? Which standard deviation is bigger? This isn't a trick question. Huh? What other value?
You said A or B.
Oh, that's why you can't see it. Sorry. There we go. I'm like, why is this hard? That's why it was hard. Which one's bigger? B is bigger. Okay. So that means that while the mean is 1400, there's a wider variance from that mean. Okay. So we can go on either direction of that case. All right. That one. Okay. Find me my expected value for tossing the die. So each of those are 1/6, right? That's my probability for tossing a die? Okay. So based on what I've given you right here, can I determine what the expected value is? Okay, so find me my expected value of rolling a die. Yes.
Would it be just because it's a uniform, wouldn't it be 1, 2, 3, 4, 5, 6? Because each has an equal chance.
But your expected value is, you're still going to be able to come up with an expected value. So you're not going to have 6 expected values. We still only have 1. There is something, because it's uniform, makes your life a little easier to do it one way, but you still can come up with an expected value. Oh, it's Mario Day. So what's the expected value for rolling a die? Or are you all getting stuck on your fractions?
I got 3.5.
Mm-hmm. So we got 1/6, 2/6, 3/6, 4/6, 5/6, and 6/6, which is 21/6, which is 3/4.
Because it's uniform, when you like what if
You literally could have added up the 6 numbers and got divided by 6.
would it also be the median?
Yes, because actually, in this case, there would be a median. That only works, that's not necessarily, isn't always the same, even though it's a uniform distribution. That only works in this case because we're the actual way the numbers go. So you can have a uniform distribution where the expected value is not the median. That is possible. All right. So there's my expected value for rolling a die. Awesome. Now let's play a game with it. All right, let's see. If you roll a 1, you're losing $20. Okay. So if you roll a 1, you're losing $20. 2 or 3, you're not making anything. 4, you're winning $10. 20, you're winning, or 5, you're winning $20, and 6, you're winning $30. What is the expected value of this game? So the only difference between what you just did and what you're doing now is you're not using the 1, 2, 3, 4, 5, 6. You're going to use the negative 20, 0, 0, 10, 20, and 30. So find me the expected value of this game. Yeah. So it's $6.67. So if I charged you $10 to play the game, should you play this game?
If you want to money.
Well, you have a chance to win $20, $30. You have a chance to double or triple your money. I would make the claim that if I gave you these odds before you actually figured this out, most of you would have said, yes, I'll play this game. You have a 2 in 6 chance of doubling or tripling your money. Most of you would have taken those odds. Now, once you figure out the expected value, now the long-term thing, you're going to lose money and lose a lot. So you actually have a half, basically a 50% chance of losing money or owing me $20 extra. So if we were to eliminate the negative 20, it would have been a $10 expected value. And at that point, that would be considered what's considered a fair game. A fair game is where the expected value and the value that you are paying is exactly the same. So over time, you'd win no money and you'd lose no money. Let's do one more problem. All right. So red on a roulette wheel. Okay. Anybody remember how many numbers there was on a roulette wheel? Almost. 38. So there's 38 numbers on the roulette wheel. How many of them are red? 18 are red. And how many are other? The black or the green? 20. That would be my complement, right? Okay. So you're betting $1. We're going to make this simple. If it lands on red, you win $2. And if it lands on other, you win nothing. So you double your money if it lands on red, and you win nothing if it lands on other. Oh, actually, hold on. I lied. You actually win $1 and you lose your $1. I forgot because you actually bet $1, so technically you win $1 and then you lose your $1 that you bet. All right, so what's the expected value? So that would be your expected value. Every time you played, if you bet $1, you lose 5 cents. Yes.
What's the probability if you hit a number, a color, and like first and 12?
So it depends on where you. So when you're playing roulette, you have to put your chips where you want to play. So if you're playing red, you'd put your money on just red. If you're playing a number, so say I typically play 22. That's my birthday. So I'll put my money on 22. If I hit, I win 35 times what my money was. But I don't win because it was black, unless I put money on the black one, black too. So the way when you're playing roulette, you can put your chips basically anywhere. Like you can put it between the number 22 and 23 and play both those numbers, for example, and things like that. Huh? Yeah. So like if you put it in between it, you'd win 17 to 1 odds.
Last summer, I put 25 on 7, 25 on red, and 25 on odd, and I hit all 3.
Nice. Mm-hmm. Yep. Problem is now if you did that multiple times, you probably would have lost all your money after that point. But the smart thing is after you win it, you walk away. It's like, I'm good, thank you. That's the thing. So like, remember the girl I told you that was playing in the middle of the entire board? She was basically betting on everything. That's in essence what she was doing. She was winning every time, but she's losing that 5 cents every single time she played. She's losing that little bit. But if you start off with a couple $100, It's going to take a while before that eats away at your winnings. So that's roulette. Okay, couple more. Is this a probability distribution? Yeah. Why? Correct. It's got to add up to 1. 1/3, 2/3, 1/3 does not add up to 1. So therefore, this is not a probability distribution. And everything we just did does not work. So if it is not a probability distribution, you cannot find them. You can't find the expected value. You can't find anything. None of it works. All right, last one. Going where they actually are going to use it. So regional hospital has collected this information. I used that wonderful website to come up with my answers for these 3. So the relative frequency, X, is the number of times a helicopter is used to transport critical patients each month. It was derived from a similar sized hospital, so they basically used data from another hospital to determine this. So would that be experimental or theoretical? Yeah. What was it saying? Sorry. Experimental. We collected the data and we're using that data. So that's an experimental probability. All right. So find the average number, the variance, and the standard deviation. You can use the calculator to do all those. You do not need to do those out by hand. So we've got a mean of 2, or my expected value of 2, the average number of times a helicopter is used, standard deviation of 1.35, and a variance of 1.84. Find the probability that the helicopter will not be used at all during a month to transport patients. What's the probability that they're not going to be used at all? Yeah. 15%. There's only one, right? What's the probability that the helicopter will be used at least once? Huh? It says at least once. So that means we're looking at once and all the values after that point, which means that is the what of what we just found. That's the complement. So instead of adding all those up, we can just subtract the 0.15 from 1. So 0.85. Because that's the exact complement of never being used or at least once. Let's find the probability that the helicopter will be used at most twice. So we're going to be looking at what ones? Yes, 0, 1, and 2. So we've got 54, 64, 69.
Yeah. Sure.
I was like, I could have easily been wrong. I did it in my head. What's the probability that the helicopter will be used more than 3 times to transport the patients? More than 3 times. 0.12. Since it says more than 3, we're not looking at the 3. We're just doing the 4, 5, and 6. Good. Yes.
Will we be seeing the like greater than less than symbols, or is it always going to be written out as used before
The vast majority of them are going to be written out.
Okay.
So rarely are you going to see the greater than the less than.
Okay, so make sure I know.
Yes. Make sure you know the wording. That's why I said that the hard part's going to be the English a lot of times in these. All right. We're good.